Welcome, friends, to our first session to Senior 5 End of Year Assessment. As we come to the end of year 2025, this is the paper that we have for chemistry, and this is Chemistry Connect. So Senior 5, that is A-level chemistry, it has a code of 525/1. And today we're basically looking at this paper 1. So this is stroke 1. One other session, we shall be looking at paper 2 for Senior 5. So a standard paper, it is taking 2 hours and a half. Specifically, this paper that we are looking at, it is 2 hours and a half. We're going to go through all the numbers first, and then after we look at section A items. As I told you, we have 3 sessions to this scoring guide, where we'll be looking at section A, and then we look at section B part 1, and we'll go to section B part 2. Our guide today is Isaac Nyirimbibi. I'll be taking you through the whole of this session, and that is the telephone number that you can always use to reach out for any educational resources, practical books, and other resourceful materials. Let's move directly to section A. Now, I'll be taking you through, those are the instructions. For those who don't have the soft copy of this paper, you inbox me on the same number I've shown you, that you can be able to get this paper and you keep on following. Now, section A, the standard paper of chemistry in Senior 5, we see that in section A we have 2 items. And these ones are basically coming from that branch of chemistry that is physical chemistry. And then we have section B. Section B has 2 parts. It has part 1 and also it has part 2. Now, part 1 has 2 items. It has 2 items, and part 2 has also 2 items. And the learner is supposed to select only 1 item from part 1 and 1 item from part 2. Now, in part 1, that's where we find inorganic chemistry. And then in part 2, that's where we shall find our items about organic chemistry. So you can see the full standard paper is having all the 3 branches of chemistry, having section A, which is compulsory. So section A is very compulsory, having 2 items to physical chemistry. Part 1, section B, 2 items inorganic, and the learner is supposed to select only 1 item. Then part 2, also 2 items and from organic chemistry. So in this session, I'll be taking you through section A items. In the next session, we look at organic chemistry part 1, section B, and then the last session, we shall go through section B part 2, which is about organic chemistry. Let's go directly to item number 1. So here they're saying, Anita, a Senior 5 PCM class student at Light Vocational SS, wants to make a project of making an electronic cell. She has 2 ionic salts, potassium iodide and potassium chloride, one of which she has to choose for use as the electrolyte. It is well known to her that the salt with the higher solubility in water or less stable is more suitable for use in this project. However, she is confused of which one of the 2. So she has 2 salts, potassium iodide and potassium chloride. Okay, let's continue. When she consulted the chemistry teacher for advice, she was given the following enthalpy data in table 1 to use for self-direction. But she's failed to know how to use it, and she needs your help. So here is the table showing the data that was given to her. That is the table showing all the data. So in this table we have 4 columns where we have the enthalpy description, enthalpy value, we have enthalpy description, and also we have enthalpy value. So we have the 2 columns. The first column, enthalpy description, you have formation of potassium iodide. That is its value, formation of potassium chloride with its value, hydration of potassium iodide, hydration of potassium chloride, sublimation of potassium. We have fast ionization of potassium, bond dissociation of iodine, fast electron affinity of iodine. We have fast electron affinity of chlorine, and then we have bond dissociation energy of chlorine. Now, when we look at this item, we run very fast to thermochemistry. Thermochemistry is part of the topics we deal with under physical chemistry. And when we look at this item clearly, we see that this item, we are looking at enthalpy changes. And when we look at these enthalpy changes, we need to be knowing what each of these mean. If it is formation, we can't pass this item unless we know the definition and interpretation of these terms that they have given us, the enthalpy descriptions. So if you talk about formation of potassium iodide, we need to be knowing what is enthalpy of formation. If you talk about hydration of potassium iodide, we need to know what hydration of a substance is. Then we see sublimation, what sublimation is. We see ionization, what ionization, fast ionization energy is. We see bond dissociation. So as we go through this item, we have to have it on our mind, the definition. Can we define all these? Can we interpret them? Can we be able to write some equation to reflect if it is bond dissociation of iodine? Can we write that equation? So those are things we shall be looking at in this item. So the quest task, let's look at the task. So the task has been divided into 4 parts, and first one is saying that as her fellow chemistry student, help Anita to, part A, analyze the data she has to construct a suitable. Now here they're saying that to construct a suitable energy diagram to determine lattice energy of each electrolyte. Identify the most suitable electrolyte for use in her project basing on stability. And then state the reason for your suggested choice. Then part C, know the enthalpy of solution for each electrolyte using Bonn-Haber cycles. And then finally, comment on the results and recommend Anita on which salt she should use for her project. Now, so we can see there are 4 tasks, and you can first pause at this. You try out this number. You try each and every task, so that as you look at the solutions, the suggested responses, we see whether you have passed or not. You can even score yourself and see whether you have passed or not. Now, let's go directly to part A. For part A, they are saying that help Anita to analyze the data she has to construct a suitable energy diagram. So, how many diagrams do we know? Or which other methods can we use to solve such? We are looking for lattice energy. If you are looking for lattice energy, which diagrams can we use? The lattice energy. So we have the potential energy diagrams. We have the Bonn-Haber cycle. We have Bonn-Haber cycles. We can also use the consolidation method, where we will use the thermodynamic equations. So we can use that method of consolidation. cancellation. So you have all the three methods. Which one is simple for you? Here they have not been very specific on which one you are going to use, but it's upon you to tell us the one that you're going to apply, and then the one which is very easy for you. But for this case, I want us to go to use the potential energy diagram. Then also Bonn-Haber cycles, there's an item which wants us to use Bonn-Haber cycle. We shall be able to see how to use. I believe from wherever we are, we have done some items which involve the cancellation method. Now, I have summarized the enthalpy descriptions here. Enthalpy of formation of potassium iodide, enthalpy of formation of potassium chloride. So I have summarized all of them here, and we're going to be drawing the potential energy diagram. So we can put a small subheading and we say, you recall part A was saying, analyze the data she has to construct a suitable energy diagram to determine the lattice energy of each electrolyte. Which electrolytes are we having? We have in the question the potassium chloride and the potassium iodide. And we want to know which one is the best. Which one can they use as the electrolyte? So let's see from our summarized data. We are going to start with potassium chloride. So you can say the potential energy diagram, potential energy diagram to determine lattice energy, of potassium chloride. So that is our first diagram that we are going to draw. I want to move step by step so that you can go out there and you try out other items about determination of enthalpy. It can be for lattice energy, it can be enthalpy of formation, depending on what they have asked. In this case, we are looking for the lattice energy. So let's see. We want to make sure that we can see very well what we want. Okay, I want it to be thicker so that we can be able to see exactly what you want. So the potential energy diagram, we are going to have, so we can draw a line up here, line here, and then, so in this area, we are having the potential energy. This is where we're having potential energy. This is very thick. Maybe they can reduce. So they have potential energy in kilojoule per mole. Now we are going to start. Where do we start from? I want to extend a little bit up, and we see. So we are looking at potential energy. This is the potential energy diagram for potassium chloride. Now we are looking for lattice energy of this salt, potassium chloride, and we are asking, where are we starting from? So on this is our potential energy diagram, and in this area we are having the potential energy, and let us say this is our initial area at 0. So since we have enthalpy of formation of potassium chloride, we have it here. And we say that enthalpy of formation, if you talk about enthalpy of formation, this is the energy change when 1 mole of a substance is formed. So it is 1 mole of a substance is formed from its elements in the standard states. So what are the elements in potassium chloride? We have potassium, and the standard state of potassium is a solid, reacting with chlorine, and you recall chlorine exists as a what? A molecule, to form potassium chloride. but the energy change for formation of potassium chloride is negative 436. So if it is negative, which means negative will come down here. It is in the negative side. So this will be negative 436.7. So which means if we are to put our result where it is up to here. That is where we have our product, which is potassium chloride. But is this equation balanced? No. In the product, we have one chlorine atom. In the reactants, we have two chlorine atoms. But from our definition, we are saying that it is the energy change when 1 mole of the substance is formed. So since it is 1 mole which is being formed, when we are balancing, we can't put anything on potassium chloride. Instead, we come and make this one a half. So when you make it a half, this one becomes 1 chlorine atom, 1 chlorine atom, 1 potassium atom, and then 1 potassium atom. That stage, we are okay. Then we move on. Now, we have, what do we have? We can start with maybe potassium. We have enthalpy of sublimation of potassium. It is here, 89, positive 89. And we say that enthalpy of sublimation, here we are, from the word sublimation, we are forming from a solid to a gas, which means we shall be having potassium in gaseous state. And this one they are saying it is positive 89. Now, for this one, for chlorine, we have not touched it, so it becomes plus a half chlorine gas. Then there's something we know about potassium still, the ionization energy. The first ionization energy of potassium is positive 419. Now, you recall here we have reached at 89, but the first ionization energy of potassium is 419. So which means we're going to get 419 plus 89, and then we'll be able to get the product, the final value, where we're going to get our product when first ionization energy takes place on the gaseous atom of potassium. We know that ionization energy is the amount of energy required to remove 1 mole, to remove 1 electron from a gaseous atom. So this is the gaseous atom of potassium, and I'm putting that. And then when we get 419 plus 89, what do we get? Get your calculator. You can add and you see that you'll be able to get 508. So from 508, we have gotten the one for, you recall at this stage, we are moving from potassium. At this stage, we are having potassium ion still in gaseous state. And then this one have not touched it, it remains chlorine gas. Are you seeing that? Okay. Now, can we do anything else on potassium? No. You recall, when we talk about lattice energy, we're looking at the amount of energy required, that amount of energy when 1 mole of a lattice substance, of a crystal substance, is formed from the gaseous ions. So potassium is already having positive 1, and I believe that is the only electron it can lose. So it has only fast ionization energy, which means now we can go to chlorine. Now for chlorine, they have told us something about chlorine, that bond dissociation energy of iodine, we have bond dissociation energy of chlorine. When you say bond dissociation energy, is the amount of energy required to break 1 mole of this substance into its gaseous atoms. So this one become 2. That is the bond dissociation energy of chlorine. That 1 mole, the energy change when 1 mole of this substance is broken down into its gaseous atoms. So which means we are going to come on chlorine, and then we move. It is positive 243, which means we're going to get 508 plus 242.3. What do we get? But you recall, let's first see if it is at this point. We want to see which value. Do we just add that? You recall when this one forms the gas, when this one it is undergoing bond dissociation energy, we are going to form a gaseous atom. You recall this half which is behind chlorine, it is with these two, will go with these two and remain with one chlorine atom, which means for this one is going to form chlorine gaseous atom like that, plus of course potassium. Now it is moving with this one, it has not been touched. Now you look at this, the original one, we are forming two chloride atoms, or we are breaking one more, but here you see we are breaking a half. So which means the value here, which is 242.3, instead of using this, we are going to use half, because it is half of this that has been broken down in this case. So which means we're going to add a half of 242.3. Those who have calculators, you can get that. A half 242.3. That is 121.15. So which means when we get 508 plus 121.15, what do we get? We shall be able to get 629.15. So that is the value that we have at this stage. Hope that one is clear. Now, after the atomization, then we have the electron affinity. First, electron affinity. Electron affinity, that is the amount of energy required to do what? Here we are adding electron to the gaseous atom. So which means we are adding an electron. If you have chlorine gas, we are adding an electron to form chlorine ion, still in gaseous state. So that is what we are looking for there. So which means, but which value did they give us? Negative. Now which means here we are going to subtract on this total that we have gotten here. We get this total minus. Okay, we add, but when, of course, when we add this, it will be like minus 347. What do you get? Get your calculator, and we see when you get 629.15 minus 349, what do we get? So we get 280.15. Where is 280? Is it between this here? No, it is above 89. 200, it should be somewhere there. So it is 280.15. So we come at this stage. So that is it. That is it. That is it. That is it. At this stage, that is where we are going now. So at this stage, that's where we have chlorine gas plus potassium, also a gas. So we have chlorine ion, and then plus that one potassium ion. So when we reach at this stage, we have chloride ion, we have potassium ion. What are we remaining with? Which means when we get this, we add them and we get this product of ours. That is the lattice energy that we are looking for. That is here at this stage. So when you bring this up to here, that is our lattice energy. And that is what they want us to look for, the lattice energy. So how do we get this lattice energy? So at this stage, it is 280. But you recall we are moving in opposite direction, in a negative direction. So which means we are going to get this 280, our lattice is going to be the 280.15. Of course, it is minus because we are moving from here. Let's see it very well when I use a red pen. I'm moving from here, coming. At this stage, when I reach at 0, that is our 280.15. Then from 0 up to here, we are adding another one, minus 436.7. What do we get? So when we add up that, we get negative 716.85 kilojoule per mole. So the lattice energy of potassium chloride. So you can conclude and say, therefore, the lattice energy of potassium chloride is negative 716.85 kilojoule per mole, and you pass. So when I'm scoring you, what do? We come here and we see at the first stage, this is the formation, so you get a score there. Then we have at this stage, 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 and finally we have our final answer. How many scores are those? This one was giving you around 60 scores. So you can see how we have been able to get our potential energy diagram, or to determine lattice energy of potassium chloride. Hope that one was very, very clear. For those who have not watched our session about thermochemistry, there is a session about thermochemistry that I was defining all those enthalpy changes. Please get time and you go through that. Now I want us to go through the potential energy diagram. Now let's look at the second one. The potential, you go back to blue. The potential energy diagram of potassium iodide. Not ICT, this is K. Potassium iodide. Potassium iodide. So still, we do the same thing that we have been doing. So we come and draw our line. And as we said, this is the area that we have potential energy in kilojoule per mole. That is our potential energy. And now we can start from 0. Since we are looking at potassium iodide, we can start with the formation of potassium iodide. The formation of potassium iodide. So if this is our 0, potassium iodide is formed from potassium, which is a solid, reacting with iodine, which is a gas. Iodine exists as a molecule. So since iodine exists as a molecule, so we put iodine with a 2. And then what are we forming? Our product formation of iodine, negative 327. So here we have negative 327.9. So at this level is where we can put our product, which is potassium iodide, a solid. Then we start on our journey. So we start with now sublimation of potassium. I believe now we know when we talk about sublimation, and we see that is 89. At this stage, we are moving to potassium gas. Hey, but first wait, before we continue, we have not balanced our equation for formation. Potassium reacting with iodine to form potassium iodide. Formation is when 1 mole of a substance is formed. So which means for us to balance this, we put a half. We put a half there, and that becomes our balanced equation. So here we continue plus a half iodine gas. So this is on potassium. Are you seeing that? Now we do the same on, we continue with potassium. Now when you go to fast ionization energy of potassium, when it is gaining, when it is losing the electron, we see it is 419. So 419 plus 89, we get 508. So which means we'll be having potassium ion still in gaseous state plus a half. This is our iodine gas. So this is our arrow showing where we are moving. So from potassium in gaseous state, then to potassium ion. So now, for potassium is done, we can now deal with the iodine. Iodine, we have something about iodine, the bond dissociation energy of iodine. And we say that bond dissociation energy, that is when 1 mole of this covalent bond is broken down into its gaseous atoms. That is bond dissociation energy of iodine. Now, when you look at this, one, we shall be having, this is the iodine in gaseous atom. Of course, for potassium, we are not touching it. Now, are you seeing that this will be balanced? So 1 atom. Now, here we are forming 1 atom, or a half of iodine molecule is being broken down. Yet, originally, what was given to us is 1 mole, which means in this case we are going to add a half of the value they have given us, a half of 151. When you divide that, what do you get? 151. When you divide it, you get around 75 point something there. So you can use our calculator. So when you divide this by a half, then you get 508 plus what you have gotten here. You'll be able to get this value to put here, which will be 583. Oh, sorry. Let's rub something here. Okay. So we are saying that here we get 583.5. So that is our final value when this iodine is undergoing bond dissociation energy. Now, we continue to the first electron affinity of iodine. Now, for it is negative, which means we are going to get 583.5. We add this negative, which means we'll be coming down again. Now, when you get that plus negative 295, what do you get? So you get a value around there, 288.5. You can't put this 288.5 up here because it is below 508. So at this point, when we move like that in the same line, I believe that is where we shall be. And then you come and you get our product there. So here we'll be having ion in gaseous state plus potassium ion, which is also in gaseous state. And at this stage, we can be able to get our lattice energy when we move from those gaseous ions and come to our product here. That is our lattice energy. Are you seeing that? So we are just going to calculate the lattice energy, and here we can just say that lattice energy is equal to, so from this point we see it is 288.5, but since we're moving in the opposite direction up to 0, it becomes negative 88.5 plus. So from 0 up to here, we already have that value, which is negative 327.9. What is the answer? Negative 616.4 kilojoule per mole. And we get our lattice energy. So I believe we have managed to get all our scores. Now, when we are scoring this, we say that at every stage you get a score. At this stage, you get a score for formation, for sublimation, we have for ionization energy. We continue up here. We have for bond dissociation energy. We have for fast electron affinity. And then finally, we have the score for lattice energy. You get all the 6 scores. So you can see how easy it could be for you to get all the scores for the potential energy diagram for potassium iodide. You can use another method. We say that you can even use the Bonn-Haber cycle or cancellation method, and you get still the same answers. Okay, let's go to part C. Now, part C, they're saying, before you go to part C, that was part A. Let's look at our second part. So, part A, they are saying that analyze the data she has to construct a suitable energy diagram to determine the lattice energy of each electrolyte. So, we have finished determining the lattice energy for potassium chloride and for potassium iodide. Now, part B, identify the more suitable electrolyte for use in her project basing on stability. State a reason for your suggested choice. So, how do you know the best electrolyte? You come back to the scenario. Let's look at the scenario here. So, they say that it is well known to her that the salt with higher solubility in water or less stable is more suitable for use in his project. So they're saying that the one which is less stable or the one which is more with the higher solubility. Now let's look at ours here. We have this is potassium iodide having negative 616.4. That is its lattice energy. And then we also have potassium chloride with negative 716.85. And now they are asking which one will be the best. According to you, what could be your response? You can note down your response before we continue and we see what is your response. Don't forget to always put in the comment section your thoughts. Put there your thoughts and also let us know what is your take on that. So when you look at this, we can see that potassium iodide, it has a smallest lattice energy, and therefore we are saying that it is the better, is the better electrolyte she can use. It is a better electrolyte because of its lower. It is because of its lower lattice energy. We have seen the one it has, while the other one for potassium chloride has negative 716. So because of its lower lattice energy, that allows greater ion mobility, which allows the ion mobility, and higher electrical conductivity. Or since we are looking at something which is soluble, a substance which has a lower lattice energy, it allows it to ionize more completely in solution, which means it is more soluble. It is more soluble compared to the one with the higher lattice energy. So that's how we could explain this, that potassium iodine is a better electrolyte because of its lower lattice energy that allows it to ionize more completely in the solution. Let's go to part C. Now, part C, what is it saying? Part C. So part C, they are saying that help Anita to know enthalpy of solution for each electrolyte using Bonn-Haber cycles. Enthalpy of solution of each electrolyte. But now they're saying we use a Bonn-Haber cycle. Okay. So let's see how we could do that. Let's come back here. So there are two electrolytes. Let us start with the Bonn-Haber cycle of which one can we start with? Maybe potassium chloride. Now, we have Bonn-Haber cycle for potassium chloride, and then we are going to draw another one, the Bonn-Haber cycle of potassium iodide. Now, we can start with what we know. What we know about enthalpy of solution. When you're looking at enthalpy of solution, we look at two things. Enthalpy of solution involves the lattice energy. It also involves, okay, let's look at it. Enthalpy of solution is equal to the enthalpy of lattice plus the enthalpy of hydration. So those are the two things. Do you know the formula for writing the lattice energy? Do you know the one for hydration energy? And do you know the one for solution? So those are the two things that we need to think about. So when you're drawing our Bonn-Haber cycle, we start from what we know. If you're looking at solution, which means the one for solution is the one we're looking for. And if it is potassium chloride, meaning we are going to be having potassium chloride, which is our solid. We dissolve it in water, aqueous. When you dissolve it in water, it will form potassium ions, aqueous, plus chloride ions, which are also in aqueous state. Are you seeing that? Now, this is what? Enthalpy of solution. The one we don't know. This is the one that we are looking for. Now, we are going to use, you recall in the question, they have already given us, we have already calculated the lattice energy. And we have been given the hydration energy. But now the question is, what is hydration energy and what is lattice energy? Now, for lattice energy, you recall we have lattice energy which involves bond breaking, the one which involves bond breaking, and we have the one which involves bond formation. Bond breaking, and then we have the one which involves bond formation. Now, the one we have been looking at, it involved bond formation. Now, this one, which means we're going to involve bond breaking, where a crystal solid is breaking into its gaseous ions. This is chlorine gaseous ions. So the one we had was from gaseous ions to this solid, which means if we have our lattice energy for potassium chloride, which is here, negative 716, instead of it being negative 716, it will change the sign. The sign will change from negative, and in this case it becomes positive 716. 716 point, that is 716.85. So If it is from the gaseous ions to the solid, it is a negative, the one we got. But this time now, since we are moving from the solid to gaseous ions, now it becomes bond breaking, which is positive. Now, what is hydration energy? Now, the hydration energy, it is the one when a substance is completely dissolved in enough solvent. But which ones? The gaseous ions are the ones which are dissolved in enough solvent to form the aqueous ions. For example, if we talk about like potassium, if you're talking about like potassium ions, we dissolve it in aqueous to form potassium ion aqueous. But this time around we are having the two, potassium ion and chloride ion, which means when you have this up to that, that is the one, the enthalpy for hydration. And we have the enthalpy for hydration as negative 685. They had already given it once. We already have that one. So I want to remove this so that they don't disturb us. Okay. Okay, now let's look at our diagram very well. It is there. We can also remove this. So you call that this is our lattice energy. I want to use blue so that you can differentiate. So this is our lattice energy, but which involves bond breaking. And we have seen it is, we have already calculated it up there. Then this is the enthalpy of solution that we are looking for. So we have direct route and the indirect route. So direct route is the enthalpy of solution, which is here. But we have this indirect route, this one, which can come like this. I believe we call that. And we know that the direct route, which is enthalpy of solution, will equal to the lattice energy, which you have, plus the enthalpy of hydration. Enthalpy of hydration. So we have, this will be positive 716.85. We add the one for hydration, which is negative 685. What will be our answer there? It will be positive 1.85 kilojoule per mole. So that will be our enthalpy of solution for potassium chloride. Then we can also look at the one for potassium iodide. We still do the same. Now, since we have already looked at this, now the one for potassium chloride becomes much easier for us. So for potassium iodide, which means we shall be having potassium iodide, which is a solid. We dissolve it in water, aqueous, to form potassium ions, aqueous, plus chloride, plus iodide. Let's remove this, plus the iodide. Still also aqueous. Now this is the enthalpy of solution. Then we also look at the lattice energy, which involves breaking. The crystal lattice, the solid will be breaking to its gaseous ions. Even here we have chloride, gaseous ions, and this lattice energy, we have it. The lattice energy, we have it as, now the other side was negative, now here it becomes positive 6.4. Then from gaseous ions, it will be moving to this direction to form the one with enthalpy of hydration. So which means in this case we have the direct route here. This is our direct route, and then our indirect route will be that. So which means our direct route, the enthalpy of solution will equal to the lattice plus the enthalpy of hydration. So enthalpy of the lattice is positive 16.4 plus hydration energy. They gave it once. The hydration energy was negative 628. So this becomes negative 628 negative 11.6 kilojoule per mole. Let me hope that one is very clear. We have managed to draw the Bonn-Haber cycles of, this is the Bonn-Haber cycle of potassium chloride, and here we have the Bonn-Haber cycle for potassium chloride. And what was our next question? So our next question was saying, let's look at it. Comment on the results and recommend Anita on which salt she should use for her project. So we have seen the enthalpy of solution for the two, and they want us to use the same results to advise Anita on which electrolyte she can use. So we have the two. We have this for potassium chloride. We have this for oh, sorry, that was a mistake here. This is potassium, this is chloride, not chloride. Okay, sorry about that. So this is supposed to be potassium ion and then the iodine ion. So this is because when you get that two, we get that, and that will be the enthalpy of hydration. Sorry for that. Now let's look at that. When you compare the two, this value here for potassium chloride is positive 31. For potassium iodide is negative 11. So we can see that for potassium iodine, it dissolves in water by doing what? It dissolves in water. Is it exothermic or it is endothermic? For it, it dissolves in water by releasing. It dissolves in water by releasing, while this one dissolves in water by absorbing heat. So one is absorbing heat, which means it is endothermic. For the one which is releasing heat, we call that one an exothermic reaction. What does it mean? So the one which is absorbing heat, which is potassium chloride, it means that it is slightly less favorable to dissolve, while the one which is having negative, which is releasing heat, it is more easily, it dissolves more easily and is more energetically favorable. So finally, we can advise Anita. Anita can be advised to use. Anita can use potassium iodide, since it is the better choice, because it dissolves more readily in water, producing more ions for conductivity, making it a more efficient electrolyte. So we have used the enthalpy of solution. We have also used the lattice to explain. So you can see that you can advise basing on the two. And we say that when the lattice overweighs the hydration energy, meaning that that substance is insoluble or is not more soluble compared to the one whose hydration is outweighing the lattice energy. I want to pause it at that, and then we go to item number 2. So that was item number 1. I believe we have managed to go through it very well, and we have learned 2 things. We have learned about the Bonn-Haber cycles. We have also learned about the potential energy diagrams. So So those are two things that we have managed to look at. So let's look at item number 2. We see how best we can also wind up with it. As I said, let's keep on pausing so that you can note down some of these questions for those who don't have. But in the comment section, you can also find these items. All these items have been put in the comment section there in the description. Check in the description section, you'll be able to find these items, and then you can even first try them out. Try them out first before you go through this scoring guide. So let's go through item number 2 and we see how best we can wind up with it. As I told you, for those who have not yet subscribed, you're missing a lot. Click on that subscription button and don't forget to click on the notification button so that whatever we share, whatever we publish, you're able to get it as the very first person. Otherwise, you'll be missing out some things. Why? Because you have not clicked on the notification button. And even when you find that this has been helpful, don't forget to also share with friends so they can also keep on learning from whatever we discuss. Let's look at item number 2. Agrotech Minerals Limited has developed a new inorganic fertilizer labeled X in hydrated form. Laboratory analysis shows that the solid contains 9.37% magnesium, 10.93% nitrogen, and 42.18% water of crystallization, and rest being oxygen. Molar mass of X is 256 grams. 5.0 kgs of fertilizer was available for sale. The manager thought to know the amount in mass of nitrate nutrient in X that would be delivered to maize. Keen to know about environmental hazards, X was burnt in absence of air and decomposed with brown gas in nitrogen dioxide according to equation. So the equation is there. Magnesium nitrate decomposing to form magnesium oxide, nitrogen dioxide, and oxygen gas. So the company thought to know the volume at STP, of the brown gas produced from burning 1.0 kg of fertilizer and assess the environmental impacts of the emissions and mitigations. Due to available rocks containing magnesium in the area, the company manager further seeks to evaluate the industrial synthesis of the fertilizer X from magnesium oxide. So you have magnesium oxide and nitric acid to form magnesium nitrate, which is our fertilizer, and the water. The supplier reported that he would potentially supply 10 kgs of magnesium oxide per day, and the manager intends to know how much fertilizer would be available in 1 month, and also possible environmental impacts of using the fertilizer and mitigations. As a learner of chemistry, help the company to know the molecular formula of compound X. Let's start with that. The molecular formula of compound X. You recall they have given us some data up here about this X. It is hydrated. They have given us the percentage composition of elements present and even water of crystallization plus the molar mass. So if we have all those, I believe we can be able to respond to them. So let's go direct to our area where we are doing our solutions. So let's look at this. So the item 2, part A, they are saying we calculate the molecular formula of compound X. Now this is the information that has been given to us. They have given us the percentage composition and they have also given us the molar mass. So I want us to go through that very fast, and we see, I believe now, if they have given us, this is magnesium, nitrogen, water of crystallization, rest being oxygen, we can first calculate the percentage composition of oxygen, which means it will be 100 minus the sum of the other ones, 9.37 plus 10.93 plus 42.18. What is the answer? So the answer for that will become 37.52. So that becomes our percentage composition of oxygen. So before we look for molecular formula, we need to first get the empirical formula. Empirical formula of X. How do we get empirical formula of X? We can draw our table. We say element. Which elements do we have? We have magnesium. We have nitrogen. We have oxygen. And we have water. So at that stage, so we can have that, and then we can draw our lines very well. So we have our line here, we have for magnesium here. Don't worry about the lines if they are crooked. Okay, so we have the symbol. Let's also look at the symbol, but we are going to be fast. Symbol is magnesium, we have nitrogen, we have oxygen, and we have water. From there we go to what? We have go to the percentage composition by mass. So percentage composition of magnesium is 9.3 what? 7. Then for nitrogen, that is 10.93. For oxygen, we calculated it at 7.52. Water, that is 42.18. Okay. Then we can move on. From there, we can go to the number of moles. We know that number of moles is equal to the given mass, which is 9.37 over the molar mass. Molar mass of magnesium, that is 24. And when you divide that, you get 0.3. I recommend we always use 4 decimal places to avoid errors. So here it becomes 10.93 over nitrogen, that is 14. So that the answer becomes 0.7807. Then here we have 37.52 over 16. There we get 2.3450. And then here we have 42.18. Now for water, we get the one for oxygen, which is 16 plus 2, and that becomes 18. I believe you know how to get that in senior 5. You should be able to know that. 3, 4, 3, 3. So that is the number of moles for each of the elements present. And then finally, we look for the simplest ratio. Now, when you're looking for simplest ratio, we look at the number of moles for each of the elements present, and then we divide by the smallest. Which one is the smallest? We have this, that, this, and the other one. So you can see the one for magnesium is the smallest. So it will be 0.3904. We divide by 0.3904, which will give us a 1. So here we have 0.988, no, 7807 over 0.3904. What we get? Here we are getting a 2. Use your calculator also and confirm whether they are the same values you're getting. So you have 2.3450 divided by 0.3904, we get a 6. Then 2.3433 over 0.3904, we also get what? A 6. So I believe from there we can be able to write the empirical formula. So which means the empirical formula here will be the nitrogen. I think we can rub a little bit here. So such that it can fit. I want to see how we can fit it very well. So the empirical formula becomes, it is magnesium, it is 1, nitrogen, there are 2, oxygen, there are 6, water, there are 6. So which means we can arrange it as A-level learners. We can see that that is magnesium. When we remove a 2, we factorize a 2, which means we'll be having N, or 3, we factorize out a 2, and this is water of crystallization. We normally write water of crystallization in that manner. So that becomes our empirical formula. But we need to look for the molecular formula. So after getting the empirical formula, then we can also calculate the molecular formula. Let's use this earlier. So we know that the molecular formula is equal to the empirical formula times N. And we say that this N is equal to the molar mass over empirical formula mass. So the molar mass, they have given it to us as 256 over the empirical formula mass. Now this is where we come and we use our empirical formula here. That is magnesium nitrate hexahydrate, and then we look for, so that is magnesium, that is 24 plus nitrogen, it is 14 times 2, which is 28 plus. Now there are how many atoms of oxygen? 6 times 16, that becomes 96 plus 6 times water we have seen is 18. What is 18? 18 times 6, that is 108, which is equal to 256. So which means here we divide by 256 and the answer becomes 1. So N is equal to 1. So the molecular formula will equal to, so we have magnesium nitrate pentahydrate, then we multiply by a 1. So when you multiply by 1, it will remain as magnesium nitrate pentahydrate. Some learners, because N is 1, some learners tend to end here. When you end here, you don't get all your scores. So for when we are scoring this, you see that we are giving you some scores here. For determining the moles, we give you a score. Empirical formula, we give you a score. For N, we get a score, and this one we also get a score. So you see, at the end of it all, you are able to get all your 4 scores. You see, you get all your 4 scores. So please, I want you to keep on practicing so that you are able to get all the scores very well. Okay, now let's go to the next question. Part B. Part B was asking to find the mass of the nitrate nutrient. It is here. Mass of nitrate nutrient in X. Now, X is a molecular formula of X is here. We have already determined it. And now they want us to determine the mass of the nitrate nutrient in X. How do we get the mass of the nitrate nutrient? I want us to go a little bit back. Here they are saying that let's go back here in the scenario. As I said, here the molar mass of X is 256. Then 5.0 kg of the fertilizer was available for sale. The manager thought to know the amount in mass of nitrate nutrient in X that will be delivered to maize. So we are having a total mass of the fertilizer present is 5 kgs. So since we have the total weight of this is 5.0 kilograms. Now if we have 5.0 kilograms and you want to know the nitrate, you can see the nitrate is we have 2 molecules of nitrate fertilizer, is 2. So if it is that, we can determine its mass. So its mass becomes 2 times 14 plus 6 times 16. And what are we getting? So for the nitrate, what do we get? That is 6 times 16, 96. What is 96? 96 plus 28. That is 412, 124. 124 grams. But the total mass for this, we already know it as 256. So which means mass for nitrate, mass of nitrate will be equal to the mass of nitrate we divide by the total mass of sample times 5 kilograms. So that one becomes 124 over 256 times 5 kilograms, and the answer becomes 2.4219 kilograms of nitrate nutrient. So that's one, part B, we get done with it. So when we are scoring this, we are able to get a score for determining this, a score for this, and also a score for that, and we get all the 3 scores. Then the volume of brown gas at STP from burning the fertilizer. Now at this point, when you're getting this volume, keen to know about the environmental hazards, X was burnt in absence of air and composed with brown gas of nitrogen dioxide according to the equation. Then they're saying that the company thought to know the volume at STP of brown gas produced from burning 1 kilogram of fertilizer. So it is 1 kilogram of the fertilizer. It is here. And they want us to know the volume at STP of the brown gas. So what do we do? Let's try it out very fast. So from our equation, which we have as magnesium nitrate solid decomposing to form 2 moles of magnesium oxide 4 moles of nitrogen dioxide gas and 1 mole of oxygen gas. So even here it is 2 moles. This one was given in the scenario. So when you are interpreting in terms of moles, we shall be having 2 moles of nitrate fertilizer producing 2 moles of magnesium oxide, 4 moles of nitrogen dioxide, and 1 mole of oxygen gas. But what is our point of emphasis? Our point of emphasis is on the fertilizer and the gas which is being produced at STP. So when you are to interpret this, we can say that 2 moles of fertilizer decomposed to produce 4 moles of brown gas. But we know that 1 mole of gas at STP occupies 22.4 decimeter cubed. And also this one, if we are to put it in terms of mass, we know that we have already calculated for this one, magnesium nitrate. So 1 mole is equal to 1 mole of the substance is equal to its molar mass. So what does it imply? It implies that if we are looking at 2 moles in this case, this one, let it first go off. We shall be looking at it later. So let it go off. So we are saying that if we have 2 moles of the fertilizer, if you get the mass of the fertilizer, which is magnesium nitrate, but we are seeing that there are 2 moles, which means this one, when you get it, when you calculate it, you see that it is equivalent to 9296 grams, which will be equal to the 2 moles. So instead of writing 2 moles, we can say 296 grams of fertilizer decomposed to produce 4 moles, but 1 mole. So if it is 2 moles, 4 moles, to be 4 times 22.4 decimeter cubed of brown gas. What about 1 kilogram? Now 1 kilogram is equal to 1,000 grams, because this is the one which was decomposed. So if 296 grams of fertilizer produce that, what about the 1,000 grams of the fertilizer for it to decompose to produce? So it will be 4 times 22.4 divided by 296 times 1,000 decimeter cubed of brown gas, and then our answer becomes 302.7027 decimeter cubed of brown gas, and you get all your scores. So when you are scoring this, where are the marking points? Someone has been able to interpret, that is number 1. They have calculated the mass, that is number 2. Then they know how to substitute, number 3, and then the final answer is number 4. You get all the 4 scores. Then part 2 was asking the impact of the brown gas. The brown gas is nitrogen dioxide. Nitrogen dioxide gas. What are some of the impacts of the nitrogen dioxide gas. So I'm not going to explain, but we can explain them. But we have the first point, which can be under the air pollution. We have another one which can bring about the acid rain. You make sure you explain those ones. And also another point can bring about global warming, because it is among the greenhouse gases. So you give the danger, explain it, and mitigate it. So I've put it for you such that you also, in the comment section, you also include, tell us how nitrogen dioxide can bring about air pollution, explain the point and mitigate. How can it bring about acid rain? Explain the point and mitigate. How can it bring about global warming? Explain that point and then you also mitigate. And then let's go to part D, which is our last part. Part D, part 1. Now they want us to calculate the mass of the fertilizer produced in 1 month. But you recall in the question, they told us what the supplier can supply in only 1 day. So we can convert that into month. They say that the supplier reported that he would potentially supply 10 kg of magnesium oxide per day, and the manager intends to know how much fertilizer would be available in 1 month. So if they're supplying 10 kg per day, how much fertilizer would be there in a month? So we can do that faster. So which means in this case, we shall still need our equation from our equation, which is magnesium oxide solid reacting with nitric acid aqueous to produce magnesium nitrate aqueous and water, which is a liquid. So they are looking at the amount of fertilizer which will be available in a month. So when you interpret this, this is 1 mole which is reacting with 2 moles of nitric acid to produce 1 mole of fertilizer and 1 mole of water. Now, if we get the mass of this RFM of magnesium oxide, will be 1 times 24 plus 1 times 16, which will equal to 40. So if we are interpreting this, we can say that 1 mole of magnesium oxide reacts to produce 1 mole of fertilizer. So which means 40 grams, which is equivalent to its molar mass of magnesium oxide, reacts to produce 1 mole of fertilizer. Now we need also to calculate the one for RFM for magnesium nitrate. We had calculated it as 148. So which means 1 mole of that will be 148 grams of fertilizer. Now what about the 10 kilograms? It will become the 10,000 grams of magnesium oxide. It reacts to produce 148 over 40 times 10,000 grams, which will equal to 37 grams or 37 kg of fertilizer. Now this is for only 1 day, which means in a month in a month, let's assume we have 30 days in a month. It will be 1 times 37. No. It will be 30 times 37 kgs, which will give us 1,110 kilograms of fertilizer in a month. So when we are scoring this, we give a score for someone who has calculated the mass, the interpretation, the calculation, the value, conversion, and the final answer. You get all the 6 scores. So you get all the 6 scores. Now, the last part of part D, part 2, they want us to talk about the effect of the fertilizer, and you give the solution. So the effect of this, I want to leave it for you to practice, and you give the response in the possible environmental impacts of using the fertilizer and their mitigation. So give the danger, explain it, and you mitigate it. Give at least 3 points, and you put them in the comment section, and then I'll be able to respond to you in the comment section. You can see we have section B coming up about inorganic chemistry. Let me just pass it around. You can keep pausing and you see that is about inorganic chemistry. It is there. Then part 2, which is organic chemistry, is also there. As I said, our next session, we shall be looking at section B. So don't miss out as we go through section B of this paper. It's been Isaac Nyirimbibi, of course, the one who has been taking you through this scoring guide for section A. That marks the end of our session 1, and my telephone number is there. You can inbox and I'll be able to give you this document. But don't forget to share with friend and subscribe for more. Have a blessed time. God bless.